Welcome to today's webinar provided by the Environmental Chemistry Division of the American Chemical Society. I'm Virendra Sharma, a professor at School of Public Health at the Texas A&M University. Before I introduce the presenter, please just remind, type your question in the question box, and then I will have a question and answer session after the presentation. And so today's presenter is Dr. Jerald Schnoor, and we fondly call him Jerry, and he has many titles at the University of Iowa, Iowa City. And the titles include Henry Chair in Engineering, Professors of Occupational Environmental Health, and he's also co-director of Center for Global and Regional Environmental Research. And in terms of his background, Jerry is a registered professional engineer and member of the National Academy of Engineering that he was elected in 1999. For his pioneering work using mathematical model in science policy decision for environmental protection, he testified several times before Congress on the environmental effects of acid deposition and importance of passing the 1990 Clean Air Act. And Professor Schnoor was the chair of the Iowa Climate Change Advisory Council from 2007 to 2009. That is basically appointed by the governor of the state. In addition, Schnoor serves as a co-director of the Iowa Superfund Research Program and leads the WMCAC Phytotechnology Laboratory, which specializes in using plants to help clean and protect the environment while reducing chemical exposures to humans. And other important roles which he really serves the ACS very well is editor-in-chief for Environmental Science and Technology from 2002 to 2014, and in which Jerry guided the leading journal in both environmental science and environmental engineering that's based on ISI Web of Science. His editorial writings on environmental protection have been widely assessed by the international community, and he has published 7 books as author, co-author, editor, and more than 200 research articles in different journals. He chaired the board of scientific counselors for the Environmental Protection Agency of the United States, also the Office of Research and Development from 2000 to 2004, and also the counselor on the National Advisory Environmental Health Sciences Council to the National Institute of Environmental Health and Sciences. He served as chair of the National Research Council Committee on Science for Environmental Protection in the 21st century. And he was also the chair of the 2008 National Research Council report on water implication of biofuels in the US. Basically, he has vast experience in environmental issues, particularly waters, and we are very pleased and very honored that he is giving us a talk today and this presentation. So I leave to Jerry to start this webinar. Please, Jerry.
Thanks very much, Virendra, and thanks to everybody for tuning in today. We're going to talk about water sustainability and safe drinking water, roughly in that order, beginning with water sustainability. Water sustainability, perhaps the definition to begin, the continual supply of clean water for human uses and all other living things. That means we need clean water for drinking, agriculture, industries, and ecosystems. One reason that there's an issue with water sustainability is that perhaps we're experiencing less clean water per person, and that's due to a number of factors. One, of course, is population growth. We're 7.7 billion people now, but not only the increase in population, but also where we choose to live, more and more in urban environments, more and more in mega cities, and often on the coasts. Climate change is changing the amount of water available per person due to droughts, due to storms, due to sea level rise and increases in salinity. And of course, how we use the land is very important. Agricultural withdrawals in particular and irrigation end up causing loss of water supplies, especially groundwater, and return of nutrients, which can be a pollution source for harmful algal blooms and hypoxia. Our energy choices, fracking and what we do with the flowback waters from oil development. And finally, of course, policy, pricing, and poverty. People impoverished are most affected for sure by all of these factors and have the biggest challenge in meeting clean water for each person. If we look at increasing water sustainability due to climate change plus increasing withdrawals around the world, including the United States, are a big portion of this water unsustainability. Rivers don't always flow to the sea any longer. Those which used to sometimes don't. Wells are running dry in terms of groundwater sources for drinking water. There's, as mentioned, unprecedented floods and droughts. If you live in Peru or the Andes and you depend on glacier melt for your water supply, you're in big trouble because they're losing very fast. And again, pollution is ruining many water supplies. Rivers no longer flow to the sea. The example shown here is the Yellow River in China, but there's many others, many other examples of water resources that used to make it all the way to the sea, which don't so much anymore, including the Colorado River in the United States and Mexico. When the waters begin to warm up due to climate change, and when storms become greater due to intense rainfall events, more nutrients run off. And when more nutrients run off, we have now a reoccurrence, for example, in Lake Erie, shown here in July 2014. In Toledo, Ohio, 300,000 people lost their water supply due to harmful algal blooms. We think triggered at least in part by a changing climate and more intense runoff events. One thesis, I guess, of this talk is that we need to think more holistically about water. There's really only one water. I remember when I went to the University of Texas as a graduate student, we used to self-identify as, well, I'm a water quality engineer, or I'm a drinking water specialist, or I'm a wastewater treatment person. And I tell my students, no, you're not any of those. It's all about one water supply. And when we withdraw water and return it as wastewater, that in turn has to become the new source of water for drinking and for other purposes. So this slide tries to show where I think we're heading, and that is in reduced removals from groundwater and from surface water, and more water recycling and reuse. And of course, in order to do that, we as water specialists in the ACS, we have to be able to treat the water to a very, very high standard in order to reuse it or re-infiltrate it into the ground or return it to the streams. It has to be that our reused water is water in which we try to recover energy, nutrients, and yes, water, but without the emerging chemicals if we're going to reuse it. One example of that, of course, is maybe the biggest and oldest example in the United States is the water reuse occurring in Orange County, California. This groundwater replenishment system was completed in 2009. It amounts to about 70 million gallons in the Los Angeles area, a very critical water reuse project in a very water short area. And it's used in two ways. After much treatment, microfiltration, reverse osmosis, advanced oxidation with UV and hydrogen peroxide for disinfection. About half of that 70 million gallons is put into a spreading basin to recharge the groundwater for reuse later, and about half of it goes at the lower part of the groundwater shed to prevent seawater intrusion. So this is one example of how we need to replenish groundwater supplies by treating the water very highly and returning it. One other example, more recent, in 2016, is the San Diego Carlsbad desalination plant, shown here with the banks of reverse osmosis modules. And as the costs come down on desalination, we will see more and more of it. As a last resort, water reuse is cheaper, and I would submit the first choice if possible, but eventually we may even run out of water to reuse, used water, and sometimes we have to create new water supplies by desalination. This particular plant cost over $1 billion, but it definitely diversifies the water supply in San Diego when they have so little to call their own. Some of the worst places that have been most prone to drought now are in places like Cape Town, South Africa. You may recall that last year they declared day zero. That was supposed to be on July 9th, 2018, when they would completely run out of water, fresh water supply. And fortunately, rainfall came before that date and has continued now. The situation is not quite so dire, but climate has definitely changed in Cape Town, South Africa, and the rainfall patterns have dramatically decreased at certain times of the year. The good news is that people have been able to conserve, and same as in California, now they are in a situation of using only about 50 liters of water per person per day. And that's a remarkable conservation which continues there. Of course, how we use the land greatly affects our water quality. My own state of Iowa, something like close to 90% of the land is in some form of agriculture. That means all the precipitation is flowing through soil, even if going overland, but mostly percolating through the soil and picking up soil particles, fertilizers, pesticides, and so on. Water is really water plus all the other constituents that we need to can be concerned about. And so it's incumbent on us to collect and treat and distribute the purest water we can as water professionals. Now, the traditional surface water treatment, at least here in the Midwest, consists of usually a surface water supply, a river or a lake, and the addition of chemicals for coagulation and flocculation and sedimentation of the turbidity out of the source water, followed by filtration, usually just rapid sand type of filtration, and chlorination for disinfection and storage and distribution. That would be a typical type of pattern. But sometimes we'll see it may not be enough. You might ask, well, how is our drinking water regulated then? How do we know if it's safe? And we have a system in place through Environmental Protection Agency and primary drinking water standards shown on the left column and secondary standards shown here in the right column. The primary standards are enforceable by law, and you may also know them as maximum contaminant levels. There's roughly some 80 or more pollutants which fall into this category, some naturally occurring, but many caused by humans. And they include nitrate and lead, coliform bacteria as an indicator organism for potential pathogens, and quite a few organic chemicals and pesticides. The secondary standards are not necessarily legally enforceable unless your state says so, but they can cause aesthetic problems, not necessarily human health problems, and they include iron, manganese, fluoride, pH, and so on, bromide. An example of a regulated contaminant in Iowa is like nitrate, which is too high due to agricultural runoff. And in Des Moines, we frequently exceed the maximum contaminant level, the regulated level of 10 milligrams per liter. And that's because we apply so much, over 1 billion kilograms of nitrogen to the land each year, and roughly 10 or 20%, depending on the storms that year, runs off the land and into waterways. Violations have increased in the United States, in part due to changes in rules, more stringent rules and better detection, but also in some cases due to changes in climate or changes in how we use the land. Shown in B here on the left-hand side is the total coliform violations, a very common one. Disinfection byproducts is another one, shown in A, along with nitrate and lead and some other common violations of the drinking water standards. These are regulated, and as you know, when they are exceeded in drinking water, the community water supply here has to make public notification and tell people, and also have a plan to alleviate the problem. Tell people that there is a problem and to alleviate it. On the right, you can see that violations have continued to increase, especially as we get new rules through the Safe Drinking Water Act. Lead is another regulated contaminant that's been in the news a lot, not only in Flint, Michigan, but especially there, in which lead pipes and service lines are part of the problem due to very old pipes and corrosive water. They changed the source from the Detroit River and Lake Huron to the Flint River. It was more corrosive. They didn't make chemical additions to offset that completely, and it caused greater and greater corrosion and erosion of lead from these lead pipes and faucets and solder. Shown in the upper right here is a typical lead pipe, and you can see even the lead oxide, which is formed on the inside of the pipe. And you can appreciate that those particles can break loose with changes in the corrosion potential and the aggressiveness of the water. And that can go into the household and expose people. Also, the lead oxide, when the water becomes more corrosive and less stable, they can simply dissolve these particles and also dissolve lead from faucets. This is a typical water main, and I took this one from an Iowa cross section, but you can see the iron tubercles, and when the chemistry of the water changes, these too can become unstable and break free, and they can, for example, scour lead from the service lines on the way into the house. This is not only a problem in Flint, Michigan. We really need to consider investment in our infrastructure in order to remove and replace these lead pipes. And it will occur at a significant cost, but it truly is a community health hazard. That is, when the chemistry of the water changes, and that can happen in a number of different circumstances, it can liberate the lead and expose our kids. Well, we've been talking about the regulated chemicals that EPA has at least been able to regulate for the most part, but a person may ask, what about all the other chemicals? What about new chemicals? What about emerging chemicals? We have a system for that under the Safe Drinking Water Act amendments of 1986. It's called the CCL, or Contaminant Candidate List. At any one time, currently we're on our 4th list. We have 100 chemicals and 12 microbiological agents, which have gone through a 3-step process, screening process, to be named as a watch list. That is, they're not regulated. There's not a maximum contaminant level set, or they're not enforceable by law, but they're on the list that we should consider putting a maximum contaminant level and legal enforcement on them. This list includes some pesticides, disinfection byproducts, industrial and consumer chemicals, waterborne pathogens, and of course consumer products like pharmaceuticals, and even the biological toxins from harmful algal blooms. The microbial contaminants list, the 4th list on this watch list, is shown in its entirety here. There's only 12 of them. There's some pretty significant ones, including caliciviruses, which include norovirus, a variety that you may well know about, Salmonella and Shigella. And Legionella is here in red, and I want to come back to that later on in the talk. The chemical contaminant list of 100 is too much to show on a single slide. So I've picked out just a few here that are pretty interesting and have quite high toxicity levels. Again, these are unregulated chemicals, but they're on the 4th contaminant list to watch and to try to consider whether there should be MCLs for these. I'd like to talk now for a moment about 1,4-dioxane, which is on this 4th chemical contaminant list, a solvent and stabilizer, which has contaminated an awful lot of groundwater supplies and occurs in public drinking water systems a great deal, as shown on the map here on the right. The bigger the red dot, the higher the dioxane concentration in the source water for these drinking water supplies, mostly groundwater supplies. You can see the problem with dioxane from its chemical structure on the left. Cyclohexane with 2 ether linkages in it make it very difficult to degrade, a very stable molecule, and unfortunately quite toxic. If you use the IRIS database and calculate a 1 in a million cancer risk from drinking this, you would only be able to drink 0.35 micrograms per liter. But again, this is an unregulated chemical, and this is just a calculation using the EPA IRIS risk database. Each and every state ends up dealing with this in terms of their own rules, often issuing a health assessment, often differing state to state, and leaving very little room for uniform treatment of the problem. Perchlorate is another one. We've struggled with this chemical from fireworks and from explosive compounds. There are natural sources of perchlorate, but very low levels. We've struggled with it since 1998. It was on the first contaminant list, and we continue to struggle with it. In 2011, after watching it for some 13 years, EPA decided to regulate it. And still, however, they have not been able to come to a decision on what a federal maximum contaminant level enforceable by law level should be after all these years. They have set an interim health advisory level, not enforceable by law, of 15 parts per billion. And meanwhile, each state has set different advisory levels, shown here in the last bullet. All of the states marked in gray and hash marks and black here on the map indicate problems with perchlorate. There's still another kind of unregulated contaminant, some of which are covered under the contaminant monitoring rule number 4. Once again, these are unregulated contaminants on some kind of a list in which public water supplies have to measure them in their drinking water. And eventually a decision may be made to put them on the contaminant watch list or even to make an MCL for them. Right now, the emphasis is on these cyanotoxins from algal blooms, shown in the picture on the right, and microcystin in particular, a very potent toxin. I've actually seen myself a dog die from just licking water that contains harmful algal bloom and microcystin. The cyanotoxins aren't the only chemicals that are unregulated on this list. It includes some metals, some haloacetic acids, brominated ones, alcohols, and some semi-volatile organic chemicals. Another example of an unregulated chemical in which there was no maximum contaminant level, no TSCA report on it, no safe drinking water report on it, no NPDES permit for pollutant discharge, because there was supposed to be no discharge from these tanks here of this coal washing compound called 4-methylcyclohexamethanol. And it smells like licorice. It was released in a spill into the Elk River in West Virginia just a few years ago, you may recall, and ruined the drinking water supply for some days for 300,000 people. At the time of the spill, there was no data available on this chemical. There had been pre-manufacturing data done by the company that manufactures it, but that was very difficult to get. So you end up with chemicals that are in common industrial use, but not regulated in any sense of the word. One way to address that was thought to be the Frank Lautenberg Chemical Safety Act, the first major environmental legislation we've had in some years, as an amendment to the Toxic Substances Control Act in 2016. It's a mandatory requirement for EPA to evaluate the existing chemicals. But at any one time, they can only do 10 or 20 of them. This is the current list of chemicals, and as you can imagine, these have been around and in common usage, like the previous slide, for a long time, including asbestos, bromopropane, carbon tetrachloride, tetrachloroethylene, trichloroethylene, and so on. Oh, there's 1,4-dioxane again. Well, you might ask the question then, well, Schnoor, how many unregulated chemicals are there? And can EPA keep up? And I think the answer is clearly no. If you look at the American Chemical Society, the CAS registry, there's about now 129 million organic and inorganic substances, 65 million protein sequences, and some are potential pathogens and DNA sequences in the registry. Now, not all of those are in common use. They're out of the 129 million, there's about 80,000 that are in common commercial and industrial use. And out of the 80,000, there's about 2,000 that are in high production use. That's over 1 million pounds per year manufactured. Incredibly enough, we add to the database of compounds about 15,000 new additional compounds on the CAS registry each and every day. So I think the answer I would submit, can EPA keep up? No, they can't possibly keep up with all these unregulated chemicals, try as they may. We have chemicals in our water and in our food and our environment. And I guess the subject here is it safe? And the answer is we may not know the answer to that. We know we have bisphenol A. We know we have glyphosate. We know we have PFOA. We know we have polydiphenyl ethers, not all getting in through drinking water. Some exposures are even through contact with flame retardants in our draperies and carpeting and furniture coverings. But there is some epidemiological evidence that suggests that all these chemicals in our water may be causing certain types of disease, more subtle types of disease that are normally regulated, but they include, for example, bladder cancer implicated in our disinfected water supplies from disinfection byproducts. So now we're looking at a lot of endocrine disrupting effects and potential problems, even at very low levels, from these unregulated chemicals in our drinking water. Here they're shown again just with some data on various health statistics. For example, in one survey in Baltimore, all 300 children born had perfluorooctanyl PFOA in their umbilical cord blood, and of course it's a suggested carcinogen. Most all mother's milk in the U.S. is contaminated with PBDEs, shown in the lower right-hand corner. Let's come back to this PFOA compound as particularly troublesome today. Cape Fear, North Carolina, and Wilmington, North Carolina have recently dealt with the issue of not PFOA, but rather the chemical was sued and in court decided no longer to release PFOA, but they replaced it with a chemical called Gen X, which is a shorter chain, a 6-carbon version of a similar compound with an ether linkage here. This likely has similar type of health effects, but escapes the class action lawsuit because it's a different chemical than had been released before. The concentrations are even greater than before. We're using our courts to regulate, as you see, and that's a difficult proposition as well. EPA, once again, while it's not regulated, has set a health advisory of 70 nanograms per liter on PFC compounds in toto, and North Carolina has set their own at 140 nanograms per liter. Many of these chemicals, even though we consider them emerging or newly considered on these lists, have been around a long time. I handled a paper in ES&T by Dana Kolpin in the USGS group, which was the first ones to measure unregulated chemicals in US streams. And of course, it included some natural ones coming from humans like fecal steroids and cholesterol, DEET that we use for mosquito control, caffeine that we drink every day, but also triclosan, an antimicrobial, a flame retardant, trichloroethyl phosphate, and nonylphenol and triclosan. These are still in our water supply today and still unregulated. But often we use in the United States the courts and public opinion, social media, as some kind of regulation, since EPA really can't keep up with all of these, clearly, due to the slow rate of new rules. So triclosan, shown here, has been largely reduced, and I won't say eliminated from the water supply, but largely reduced due to the voluntary action of all of these companies taking it out of their product, and also due to some lawsuits. Now, in this case, for some of these deodorants and so forth, the Food and Drug Administration has purview, not EPA. And they finally banned triclosan from antibacterial hand soaps, but many other uses are still permitted for this unregulated chemical. Neonicotinoid pesticides have been known to be very harmful to bees and damaging the brains of bees, perhaps implicated in colony collapse disorder. A very interesting recent paper in ESNT Letters by a group here at University of Iowa showed that these pesticides are in our drinking water supply. But what's more, if you have the basic treatment that I outlined at the outset of this talk, you had rather high concentrations, relatively speaking. But if you had better treatment system, including granular activated carbon treatment and advanced oxidation, you had much, much lower concentrations in finished drinking water. And they pointed that out in a recent paper in ESNT Letters. Chlorpyrifos is an interesting chemical that also has been around a long time. It's not so much due to our drinking water supplies that were exposed, but more due to the food that we eat that has been treated with the chlorpyrifos pesticide, which is a potent cholinesterase inhibitor. There's epidemiological evidence, one longitudinal study, which is kind of hard to come by, in which they followed kids from birth all the way to age 8, that those who had been exposed to chlorpyrifos showed neurological development problems, attention disorders, psychomotor delays, and even at age 11, some tremors. Based on that evidence, in 2015, under the Obama administration, EPA decided to ban chlorpyrifos, but that decision has since been reversed by EPA under the Trump administration, and it remains despite this evidence. The stated reason was that this particular study mentioned here was not a causative. There was not cause and effect shown. Rather, it was a statistical association, as is often the case with epidemiological evidence. Several of the disinfection byproducts that have been reported in the literature are more toxic than the ones that we're currently regulating. We're only regulating the THMs and the HAAs, the haloacetic acids, but there's many other nitroso compounds and others at nanogram per liter levels in our drinking water, which are much more toxic than the ones that we're already regulating. More work to do for EPA, yes, but can they possibly keep up with all these? I guess that's the question raised in this talk. You may realize that everything we've done and everything we do with the IRIS database for assessing risk is based on single chemical exposures. But mixtures of chemicals are how they really occur in our surface waters and in our drinking waters, and mixtures do matter. They can be they can cancel out the toxicity, or they can, of course, make it much, much greater, rather than an additive sum, a multiplicative sum. And especially when one considers endocrine disrupting compounds, which can cause effects at very, very low levels, even nanograms per liter. It would be great if we had, so if you accept that this pollutant by pollutant approach is not working, and I would submit that to you, if that's not working to keep up with all the chemicals, it would be wonderful if we could come up with a screening toxicity test, which would tell us, well, this water is unacceptably polluted. And but so far, while many have been researched, shown on the right column here, there hasn't been real success in coming up with such an approach. If you ask me the question, well, what's the biggest problem of all these chemicals on the watch lists and unregulated chemicals, I would have to say Legionella. So it's a microbial one. And interestingly, it's not one that we drink in our drinking water, but it is drinking water waterborne disease because we're exposed in showers and from treated water vapor. The Legionella is notoriously resistant to chlorination, and it's virulent. And of all our waterborne disease outbreaks in the U.S., which have not seemed to be increasing, but rather have held very steady, most of those outbreaks are due to Legionella. The second greatest cause is intermittent groundwater supplies that are turned on and off, maybe in a resort or in a small community that is summertime without chlorination or disinfection. This particular slide just shows that, again, Legionella is by far the largest cause of the disease outbreak, and it's in our service plumbing, largely in biofilms. Of course, this is a big problem, Legionella in hospitals, and we have something like a 5% chance of contracting disease from the hospital when we are admitted there. Estimates of 1.7 million infected people per year, not all due to Legionella, but including disease-resistant, antibiotic-resistant organisms, as well as Legionella. Legionella are part of these pipe biofilms, and even I tell my students the pipes are like an aquarium in there. Okay, a dark aquarium, but there's organisms feeding off of the organic material and feeding off of the biofilms, and they may be involved in releasing Legionella. Legionella like hot water. They tend to accumulate in our hot water faucets, and then resistant to chlorine disinfection. Since only a couple of cells breathed in can cause the disease, they're especially a problem. Together with some great colleagues, I wrote a paper not long ago that if we make a more concerted effort at treating our drinking water, it's possible that we may not even need to contain a residual, a disinfectant like chlorine in the distribution lines if we get the food for pathogens, the organic carbon, down lower. Let me show you. We call this multiple barriers for production of safe drinking water. It's very typical of Northern Europe, especially Holland, Germany, Switzerland. Yes, they use surface waters for intake, as do we in the United States, but they insist on putting it then through the groundwater for filtration and biological action before it's actually used as a source water. We could learn from that. In addition, they spend about 3 times more on treatment, but it includes, as opposed to the early treatment system I showed, it includes sand filtration, but ozone disinfection, biologically extended activated carbon, in which the organic carbon is taken down to very, very low levels, so there's no food for pathogens. Reverse osmosis to get rid of many of these disinfection byproducts from the ozone disinfection, and also some of the salts and metals. And finally, ultraviolet disinfection, sometimes with or without hydrogen peroxide. The chlorine is a backup. It's not used. In fact, in the Netherlands, it's illegal to use chlorine in the drinking water supply as a disinfectant. They hate the taste of chlorine, and they also resist the disinfection byproducts. They don't want to be exposed to those. If you treat the water well enough and you keep track of your pipes, they also replenish their pipes more frequently. They spend more on their distribution system. than we do in the United States, you can achieve good quality water even without chlorine disinfection. Interestingly enough, we tried to compare the disease statistics and the outbreaks in both places. Very difficult to say, but certainly in Holland, there's no more disease outbreaks per capita than what we have in the US, and maybe fewer. Certainly, if we had artificial intelligence and better computer sensor systems in our water plants, we may be able to circumvent this problem of pollutant by pollutant approach. In the end, we have to order our priorities, and I guess the summary of this talk begins here. We need multiple barriers of protection, like what I showed in the example of the Northern European treatment systems. I would say as water professionals, we need to advocate for continuous improvement. When it comes to our children and our health, we shouldn't be afraid to advocate for better treatment to take society to a higher level. Yes, to argue for higher rates if that's necessary to improve our treatment systems. And of course, we need innovative approaches galore, several of which have been mentioned, I hope, in this talk. In conclusion, multiple barriers, infrastructure investment, continuously improve best practices and don't be afraid to advocate for that. We need risk-based common sense approaches because pollutant by pollutant really isn't working. And we need pollution prevention. Many of these contaminants should be kept out of the water supply in the very beginning. Thanks very much to ACS for allowing me to do the webinar, and to Virender and Kyle for introducing me. I'd take any questions if there are any.
Yes, there are a couple of questions. I'll start. Basically, some of you already covered when they asked in the beginning, but then you covered later on. You answered those questions. I'll start with the first questions. There are many chemicals you mentioned, but outside USA and maybe in Asia, they have a pollution of textiles. And you have any comments, textile dyes, you have any comments, how those can be regulated, and any comment on that?
Only to say that the question is right on. Those are, again, a group of chemicals that are largely unregulated in the United States as well. Very difficult to treat. Usually advanced oxidation processes are what we would use. Membrane processes, as I showed you earlier, like reverse osmosis, may also help with some of the dyes, but quite toxic and very difficult to treat, as the question implies.
Okay. And then these other questions about desalination, basically what is, because it generate a lot of halides and then rejection is there. So what's your opinion about the future of this approach?
That's a great question. Of course, in the case of the Carlsbad plant in San Diego, they're blessed with being located on the coast and being able to get a permit for a diffuser pipe that puts the brines, the reject waters, back out into the ocean. As the question implies, that's not without ecological concerns and considerations, but that's what is being done pretty much worldwide. Now, all of those who are in places like landlocked Iowa, like I am, and many small towns are using membrane processes and have brine reject waters. They're in a serious situation because in the past they were allowed to bleed them back into receiving streams and to get a discharge permit for that. They're no longer able to do that, and to get a deep well injection permit is also expensive and sometimes problematic. The location and the geology may not be correct. So we have a serious problem with salt worldwide. how to dewater it, how to make a useful product and recycle it like we talked about in water reuse. And there's a great room for innovation in this area. As long as we continue to use thermal desalination in the Middle East, and as long as we continue to use membrane processes, there's going to be this problem with the brines. And even living on the coast eventually may cause ecological problems with the discharge of the brines that are considerable.
Okay.
But I would say desalination because the costs are coming down, and as a last resort for a new water supply, that's the way we're going to go. That's the way it's going.
Yeah. And the next question is basically on Legionella outbreaks. You mentioned this chlorine residual. So basically, how to improve? Actually, this is from a couple of people asked this question.
I wish I had a silver bullet for that, but I would say that the first avenue of improvement is this infrastructure investment. We need to change out the pipes and the faucets much more frequently if we can't find a disinfection scheme to kill these biofilms. Now, again, the treatment system that I showed near the end of the talk, where you drive down the organic carbon, they need the organic carbon to form the biofilm and for food. So if you drive down the AOC, the assimilable organic carbon, to very low levels, that's the strategy in Northern Europe, then you should have much less of these biofilm developments in the pipe and less problem with Legionella.
Yeah, basically this leads to the next question, which was asked earlier. This may require some more money, or municipality has to put some taxes or something. And what you think what is the reality in future this may happen?
I think that's what we have to help make happen. We shouldn't be ashamed to, if greater rates are needed, to make safer drinking water for our children and for our communities. We shouldn't be afraid to advocate for that. In fact, I would say that's the role of the professional, to continue to push society forward. It is true that resource limited communities all over the world, they're also in the United States, have a very hard time with increased rates. And somehow we have to be sensitive to that at the same time. I know I'm trying to have it both ways, but that I think that's the opinion I have.
Yeah. And you mentioned several single chemicals. At the end, you also mentioned the mixtures of chemicals, and maybe we need to go some toxicity screening. So what is basically is very hard to regulate single chemical.
Yes, I think that's another reason to go for artificial intelligence and sensors, and also to try to develop toxicity screening processes, because again, the pollutant by pollutant approach, even the pollutant in mixtures approach, which we haven't even tried, can be alleviated if we had good screening methods.
And one question, maybe just maybe this is the last question, second last question. Actually, from Iowa State, someone is asking, you mentioned focus on organics, but we do have many inorganic. I think you did touch, but that's the comment is making, that there are many inorganic chemicals too in Iowa.
Yes, of course, that's certainly true. And again, more advanced treatment, as I showed near the end, will get rid through reverse osmosis and activated carbon, get rid of many of those other contaminants, inorganic, that are being mentioned.
Yeah, I think it's basically this basically more or less all the questions that came to me. and emphasis was on the mixtures, and that seems to be like a challenge how to regulate, and maybe modeling direction or toxic direction, and that what the comments are basically addressing, and most of them you have answered or gave your opinion. I think as with this, I'd like to thank you, Jerry, very much for taking time. As I mentioned in the beginning, is very much honored that Jerry took time to teach us. He's really a very admired person by the community, and we truly appreciate that he's giving us webinar and giving his opinion. He helped the community a lot, and he has been awarded the Creative Award in Environmental Science and Technology. With lots of thanks and appreciation, I conclude this ACS webinar, and thank you very much for attending the webinar. Bye-bye.
Thank you. Thank everybody for attending.